is an angle curve, just imagining varying y but holding prices unchanged. So this is in a way both an angle curve and a Marshallian demand curve. Okay, and so here, I'm just going to rearrange this thing. I'm going to multiply the expression you just saw, the Marshallian demand on both sides by P1. So that gives me, what's this on the left-hand side? Total expenditures on good 1, that's right. What is this P1 times psi? How could we interpret this thing? Okay, no, very good. So that's right. So if you want to survive, you have to spend at least this much money on food. P1 times the minimum amount of food necessary for survival. And so the minimum amount of food that you need to consume to survive is related to your basal metabolic rate. For an adult male, it's around 11,000 calories per day. So the price of obtaining those calories times whatever the calorie source is going to be something like this quantity of stuff. Okay. All right. So yes, the minimum expenditure is necessary to survive. And then this last piece is the share of your income that you're going to spend on food after you've already paid for this sort of starvation level bundle, this subsistence bundle. Okay. All right. So this comes right off the Marshallian demand that we have if we assume that you all have quasi-homothetic utility functions of this form. We get this Marshallian demand, we multiply by V1, we get this expression. So this allows us to relate total expenditures on food, per se, to some constant quantity related to the cost of a minimum bundle plus something related to total expenditures. Okay, now what I propose to do is use the data that we collected from you last week, that you guys recorded over the course of the last month, to actually estimate the parameters here that we don't know. So the things we don't know but are interested in are this alpha, this sort of share parameter, although it's no longer a share exactly, and also this sort of, we're going to treat this as a constant, which will be the minimum expenditures necessary to survive as a student at Berkeley. All right, it's a linear equation, so for those of you who are familiar with regression analysis, we can just go ahead and use ordinary least squares to estimate this thing. Here's some results. Okay, so what do I have to show you? Here's a graph. The thing on the horizontal axis are the mean daily expenditures, and the dots, each one of these dots corresponds to one observation for one of you. So there should be, maybe you can pick out your own dot on that diagram if you look closely. So I divided by, I forget how many days there were during the period. I divided by the number of days to get this into daily expenditures. I think it's a little bit easy to interpret than monthly for this. And so we get the scatter of points. You can see this kind of a positive relationship between mean expenditures. The thing on the vertical axis is mean daily food expenditures, and this green line is the best fit. It's the OLS regression line that relates those mean daily expenditures to mean food expenditures. Now the results we get are these. This is the equation we estimate. So total expenditures, that's y. I'll read this part first though. So this says that the minimum estimated level of consumption here is $8.6 per day. So the interpretation is that one ought to spend the minimum level of expenditure we see in this population at least is $8.60 for food per day, which sounds pretty reasonable. I don't think anyone here is actually quite starving, so you shouldn't interpret this as a really starvation diet. Instead, it's a pretty minimal diet. I think that's probably, I don't know, who eats, for some of you do actually manage to eat for less than $8.60 a day. This would be the intersection here. Who managed to eat for less than that? Yes. Can you tell us a little bit about your diet? Okay. Okay, that's okay. So sort of scrounging. I think if we were being precise in the diary, we'd treat the food you collected by scrounging that way as part of your income, and we want to attribute some value to it. But that's fine. You had a. What? Oh God. Okay. Okay. There's an inexpensive fast food solution. Good. Are there other people? I ate a lot of beans when I was a student. I'm not sure about. So, yeah. Right. Yeah. That's good. Yeah.
So I question about the 0.04. Is that the regression?
Yeah, that's right. So the question here is this from the regression? Yeah, these are the estimated coefficients. So 8.6 is what we're estimating to be this P1 times psi. This other parameter, 0.04, is the estimated value of alpha. This is not exactly expenditure share because of this 8.6, but this says something about the rate at which you'll increase your food expenditures as your total expenditures increase. So this is an estimate of alpha, so that parameter alpha. It's not the correlation coefficient. In an OLS thing of this sort, you'd interpret that quantity as being, we'll call it alpha hat. That's equal to the covariance, in this case, of food expenditures and total expenditures divided by the variance of total expenditures. That would be one way to compute that coefficient. But I don't want to dwell on that. So okay, so this is an estimate of this parameter alpha we had here. So alpha is equal to 0.04. P1 times psi is equal, we estimate to be equal to 8.6. And mean total expenditures per day were $66. I don't know, does that seem about right? I guess so. So the mean daily expenditures were someplace in here, around $66 per day. Not on food. That's total expenditures. And if you just look at mean food expenditures, we got a minimum of 8.6, but the average across the class was about $11 per day. Okay, so this is your angle. This is your collective angle curve. We'll estimate for E100 this year. All right. You guys have so when I did this last year, this alpha was 0.05, and it's a little bit higher, and the estimated, but this number is a little bit larger. So last year's class spent the minimum spent a little bit more, but then the rate at which food expenditures increased was a little bit greater. I didn't test it. I doubt there was a statistically significant difference between 0.04 and 0.05 though. So it's pretty consistent with what we saw last year. You guys have total expenditures on the other hand, which are quite a bit bigger on average. The average total expenditures per month for you guys were just under $2,000. For last year's class, it was almost exactly $1,500. So you guys are, I don't know, much better off than last year's class. Well, these are, how many people recorded tuition expenditures in there? Yeah, some of you did. If only 3 of you did, I think that can't account for all of it. But yeah, maybe that could account for part of it. I should say, along those lines, to calculate this, there were 2 so-called outliers that I discarded. One person looked like maybe they bought a car or something, so they had like a $20,000 expenditure this month, and the other person made a substantial financial investment. If you leave the data in here, it flattens out this curve a little bit because food expenditures don't go up, but total expenditures do. It's not, and it changes the scale of the graph or something, which is less pretty. Anyway. All right, so we got the angle curve. I want to come back, and we can use this angle curve now and the stuff we calculated here to calculate income elasticity for this class. So let's go ahead and do that. So we've got an angle curve. We just computed this. So expenditures on food in this case are equal to $8.6 plus 0.04 times total expenditures. That's expressed in daily quantities. Now I'm going to use this formula we have for elasticities. And so recall that one formula for point elasticity, I'm going to use eta is often used as an income elasticity. One formula is something like dx dy, so this partial derivative times y divided by x. Remember that prices, so in this case we're going to be interested in expenditures, not the quantity of x. So prices show up, it's just a constant. So the formula for income elasticity is here, this eta, is just equal to P1 times the expression I just wrote on the board, but we're also going to multiply and divide by P1, so you can see it actually cancels out. But the data we've got is on expenditures, not quantities. Yeah?
I'm sorry, I just can't read.
It says eta, is that because of the, yeah, sorry, okay, so it says eta is equal to the partial derivative of x with respect to y, so it's like the slope of the angle curve, times y divided by x. My P1, so I'm multiplying and dividing by P1 because the data I've got for you guys is expenditures. I know how much you spend on food, but I don't know how many hamburgers you bought. So I want to convert these quantities into expenditures I can use to compute the elasticity. And I can do that by multiplying and dividing here. You'll see how in a moment. Okay, so here, so I've got this thing here. If I take the partial derivative of px1 with respect to y, what do I get? This is the angle curve. If I take the partial derivative with respect to y, what is it? It just y only shows up here, so it's just 0.04. So this part is just 0.04. And then we multiply times total expenditures, and we have x1 here on, oh, that's not, hold on, that's a mistake. It should be P1 x1. No, it doesn't cancel because I use, oh, hold on, let's see. No, it should be, because I got the y here, I got the P1 x1 here. This is in terms of expenditures. So, there should be a P1 here. That's just a typo. Sorry about that. It went into this expression here involves a P1 because there's a P1 here. This whole expression, this partial derivative, is just equal to 0.04. So it basically went into the 0.04. Okay, so A is equal to 0.04y divided by P1 x1, so it should be divided by total food expenditures. In this case, what we have is y on average for the class equal to $66 per day. We have average food expenditures, P1 x1, equal to $11 per day. So to figure out eta at the average for the class, what we have is 0.04 times $66 divided by $11, and that gives us a result, a dimensionless result. That's the point of elasticity. There's no units of 0.24. Okay, so here's an interpretation of that. For the average, or typical I say here, but for the average E100 student, a 1% increase in total expenditures will result in a 0.24% increase in food expenditures. So for every 1% increase you have in the money you spend per month, roughly 1/4 of that will be spent on food. Yes?
I thought we were trying to find out how much the expenditures change if you change theta.
So I'm going to, okay, good question. So I'm going to use here this quantity y, which I'll call income sometimes, and total expenditures as synonyms. And the reason I'm going to do that is because I'm going to assume that you guys are solving your problem and keeping and satisfying your budget constraints. So that, for example, if it's two goods, we have P1 x1 plus P2 x2, and that'll be equal to y. So this is income, but it's also, if this holds, equal to total expenditures. Yeah, good question. Okay. It doesn't have to be, it can be as many goods as we want, of course, for total expenditures. Okay, so that's the interpretation. So for a typically 100 student, 1/4, if it's a 1% increase in total expenditures, or income if you prefer, then we'll see a 0.24% increase in food expenditures. So that's the income elasticity, 0.24. Yes? Oh, yeah, that's right. So yes, absolutely. So what we're doing here is tracing out well, I should just show you the slide again. We're just figuring out if we have a decrease, it's just coming off the slope of this thing, and at the mean of this thing, which is back here someplace, if we decrease mean daily expenditures by 1%, we figure out by what percentage, the vertical thing, expenditures on food decreases. And you can see that symmetry, just as you say. So 0.24, whether it's increase or a decrease. If it's a 1% decrease, we expect roughly 1/4 of the decrease to come from food expenditures. Okay. All right, so I'm going to take that same graph I had a moment ago now, and transform it just a little bit, so that instead of what I had, wrong way, what I had here is mean food expenditures. Recall that Engel's law, which I want to return to now, is stated in terms of the share of food in your budget. So I'm going to take mean food expenditures and divide it by mean daily expenditures. That's going to be giving me a different curve that still people sometimes call an Engel curve. So I've got the share of food expenditures here on the vertical axis and the same mean daily expenditures on the horizontal axis. So this is exactly the same mathematical relationship we saw before. We're just converting it into food shares now instead of total expenditures on food. Is that clear? Okay, so something I'd like you to notice about this is that it satisfies Engel's law. So Engel's law, which I'll fly back to that, says the poorer the family, the greater the proportion of its total expenditure that must be devoted to the provision of food. So that's what we're looking at now. And so we'll say the poorer the student maybe this time. So the poorer the student, in the sense of having lower mean daily expenditures, the larger the share of that that's devoted to food. And you can see, there's variation in the class, of course, in how much is spent on food and so on. But you can see for sure that the students who have the lowest daily expenditures are the ones who tend to have the highest food share. And conversely, the students with the highest daily expenditures tend to have a very low food share. All right, any questions about that? Yes. Yeah. So a good question. So the income elasticity that we read off this graph here, we can also think of in terms of this graph. It's going to be related to also to this. What will it be exactly? I can't do this off the top of my head. But you can relate the income elasticity to this thing as well. We're interested then in how mean daily expenditures change in percentage terms, and how this changes. I guess just how this changes, not in percentage terms anymore. It's already dimensionless. I need to work that out. But yes, there's a connection. Now here's another Engel curve. The same units here, except not daily. So these are annual expenditures, or actually GDP. So what I've got here is food share consumption. But the dots here are no longer they're no longer E100 students. Instead, these are average food expenditures within different countries. And so, and the thing on the horizontal axis is no longer total expenditures per month. Instead, it's annual GDP in US dollars. So I've got an expression. Okay, so we've got this budget constraint has to be satisfied. So annual expenditures total expenditures are close to per capita GDP. And so this tells us something about the variation in food shares across countries and their incomes. And so what I'd like you to notice about this is just that the shape of this is not so different from this. So I'll point out a couple points here. These are three-letter. Each one of these points has a three-letter abbreviation for the country next to it. So the country with the highest per capita GDP in 1993 was Japan, edging out Switzerland, I guess, there by just a little bit. So per capita GDP of something like $34,000 in 1993. Japan did not have the lowest food share. That was actually the U.S. The U.S. now has a food share of about 11% for the average U.S. household. That's pretty close to this. You can see that as you sort of move back, countries like, like Italy is an example of a developed country, but with a lower income than the U.S. or Japan. Has a slightly higher food share than the U.S. Japan, any thoughts about why Japan's food share is so high? Yes. Yeah, Japan, it does two things. It imports a lot of food, but it doesn't import enough food. They put up large protective barriers and make a lot of very expensive rice and other agricultural goods in Japan because they value something about it being domestic. So there's a lot of barriers to trade in Japan. If they had more imports, food would be cheaper. The very poorest countries in the world in 1993 are among the poorest countries now. Tanzania is the one at the very top here. It is both the poorest country in 1993 and the one with the highest food share. So the average household in Tanzania spends something in excess of 70% of its income on food. So that's a pretty big number. Here's the Philippines. Here's Thailand. Korea is here. Cyprus, Netherlands. But the interesting thing, and this is sort of why Ingalls' law is so impressive, is because this sort of relationship, this declining share as a function of total income or expenditures, holds up sort of regardless of the population you look at or the level of aggregation you deal with, whether it's students in E100 or nations of the world. Okay. All right, so switching gears. Unless are there questions about Ingalls' law or these Ingle curves? Okay. So we've got Ingle. He's one famous economist. Here's another very famous economist, Sir John Hicks. This is a statement of what's often called Hicks's composite commodity theorem. And so here's a statement of it. If the prices of a group of goods change in the same proportion, that group of goods behaves just as if it were a single commodity. Okay, so the composite commodity theorem is valuable for us not because we believe that the assumptions are always satisfied. So the assumption is that there's a group of goods. So let's imagine three goods. Let's say there's beans and rice and automobiles. Okay. Now, for me to draw a diagram on the board involving, say, an indifference curve for beans and rice and automobiles, I'd have to subject you to my attempt to draw a three-dimensional plot, and I'd like to avoid doing that. By using Hicks' composite commodity theorem, if we can invoke that, we can boil things down and make them simpler. We can say, for example, that we're interested in demand for automobiles and other goods. Okay, so this is a trick I'll often do when I'm drawing diagrams. Now, this is justifiable. Hicks' composite commodity theorem tells us when this is a justifiable thing to do. And it's justifiable when the prices of beans and rice always move together in proportion. So if the price of beans doubles, then it's also the case that the price of rice doubles, then it's fine. We can treat this demand system as though it was just automobiles versus this bundle of beans and rice. We run into trouble with this when we have goods whose prices don't covary like that. So if the price of beans went up a lot relative to the price of rice, this construction wouldn't be valid. So I'm going to sort of invoke this sometimes so I can draw diagrams that are two-dimensional on the board. Sometimes this is useful in applied analysis. As you can imagine, it works better for some kinds of goods than others. If instead of saying beans and rice and automobiles, I'd said beans and automobiles and auto tickets, it might be hard to justify the idea that those prices would all might move in tandem. But for beans and rice, it's plausible. That, if prices go up, it's because the price of agricultural inputs or land have gone up. So there's good reason to think that those prices might move together. Okay. All right, let me keep going. I have a problem that I've been encountering this year. I encountered it this morning, in fact. I live in the north of campus in the Berkeley Hills. And I moved to my new house just a couple years ago. I used to live closer to campus, so I'd walk. I like walking. Now it's a little bit too far to walk, and so I take the bus. But sometimes the bus doesn't come, like today. And sometimes I have to lecture, so I really, I really feel like I got to show up. So today I found a ride, and it worked out okay. But I can't always count on the kindness of strangers, or perhaps I can. And so one question I might ask myself, I have been asking myself, is whether I should buy a car and drive to campus rather than relying on the fickle AC transit. Yeah, bicycle, if I live in the hills, coming down would be easy, but going back would be harder. But that's another thing. I consider that also. That's a possibility. Okay, so here's the question. Should I buy a car? And so I want to think about a couple tools we might use to answer this question. You guys might be considering similar problems yourself. I don't know. All right, so I want to start this by thinking about both the costs and the benefits of having an automobile. And so what I want to begin with are some sort of thoughts about what the costs of buying a car would be. And so here's a list of a few things that occur to me that go into the cost of buying a car. If I were to go to a car lot like this one and buy a car, I'd have to pay some amount of money to actually acquire the vehicle. But